So, let us start this lecture with a quotation from Ben Sweetland, who says the world is full of abundance and opportunity, but far too many people come to the fountain of life with a sieve instead of a steam shovel, right, and they expect a little, as a result they get little. Although Buddha has told expectation is the cause of the misery, but however, expectation is very essential for any progress. So, let us now get into a discussion on our thermodynamics, and in the last lecture we discussed about basically the phase change process. In that we will also talked about not only the liquid and vapor phase, but we also discuss about solid and liquid phase, solid and vapor phase, and solid, liquid, vapor existing together, right. That we call the triple point. At the triple point, all the properties, thermodynamic properties will remain same or it cannot be changed. So, that is why it is being used as a reference point for the temperature scale. So, let us look at some data about the what we call triple point data for certain pure substances in this table. As you can see, if you look at it varies a lot, like where the carbon it is having a very high temperature, 3900, and the pressure is 10,100 kilopascals. And interestingly, if you look at the carbon dioxide, it is having triple point of 216.55 Kelvin at 517 kilopascal. 517 kilopascal means what? Something 5 atmospheric pressure roughly. Okay. And mercury, of course, it is a very what you call high temperature, but the pressure is very low, 1.6 into 10 power to minus 7. Of course, we always deal with water or the steam, that is 273.16 at 0.6113 kilopascal, very low pressure, isn't it? Is it very low pressure or not? Because 100 kilopascal is your atmosphere. So, this is a very low pressure. And as I told that this temperature is being used as a reference, that what will be the plot for the phase diagram. That means, what are the variable we can think of using the pressure and temperature as a in this plot, and what we call it as a phase diagram. And if you look at in this region, it is the solid and this region is the vapor, right. Now, if you are at here and if you go on giving some heat at this pressure, then you will be directly getting into vapor without passing through the liquid phase, and that process is known as the sublimations. But however, if increase the what you call pressure further, in case of water we have seen it is very low pressure, 0.6113 kilopascals. So, you will find a point that is basically a what you call triple point, where solid, liquid and vapor exist together. So, that is the triple point. And if you consider another point right here, let us say you are at here, and then you go on adding the heat to that solid, let us say water, if you consider. And there are two kinds of things what we can think of. One is substance that contract on freezing, right. okay, and a substance that expand on freezing, right. So, we have already discussed, that is the water which expand on freezing. That is the reason why the ice is floating on the water. Am I right? So, am I right or wrong? So, therefore, the substance, one is like that, and the rest of the most of the substances that contract on the freezing. So, if you are at the solid, then it will be converted into the liquid, and then it will be converted into vapor. That means, at this pressure it can go through all the process. Now, if you look at this phase diagram, is a very compact one, but it will not give you a lot of other things. What are those? It is not depicting or describing. Can anybody tell me? So, if you look at this line, let us say sublimation line, right, it is going directly to the solid and vapor, but there is a kind of situation where both the solid and the vapor will be existing, right, yes or no. So, that you cannot really describe in this. Similarly, for the what you call liquid to the vapor, right, there will be a wet mixtures, we cannot describe like in this diagram. And this diagram is very important, particularly for metallurgy and other things, and so also for like your steam or any other pure substances what we will be dealing with. Keep in mind this what you call triple point, the how it exists, one side is solid here and other side is vapor and this side is your liquid, right. That we call it as a triple point, isn't it? And below this triple point there will be sublimation, only the solid and vapor will be existing. But is it true for all the time, or is it true for the all the substances, or will it be different? Can I not have some solid and maybe two solid and one liquid, I can call it as a triple point? Is it possible? Or I can have two liquid point and one gas point or the vapor point, can I call it as a triple point? I can call if it is joining together, like, but is it possible for any substance, or we will go by this, triple point means three phases will be around existing independently, like, and kind of things. What do you feel? I am not getting any answer. So, let us look at that and what is happening, but before that let us look at another point, what it is critical point. Critical point, if we just go where the liquid and vapor will be coexisting, as I told in the last lecture, that at this point the specific volume of the gas will be same as that of the specific volume of the liquid. But as you go on little bit above it, let us say you are here, it is a liquid and then it will be converted into vapor, and then if you look at across that it changes, right. So, let us now look at like something a substance like which will be contracting on freezing, that is the what you call water. So, if I till now we have looked at what you call till now we have looked at two dimensional kind of diagrams, but now I have put it all the three dimensional, that is pressure, volume and temperature, right. So, if you look at this point, these are the points what you call solid and vapor region, and this region is the solid, right, and this is the line which you call it as a triple line. This is the solid liquid and this side is solid and this side is your vapor and liquid and this side is your vapor. And of course, this is the critical point where both the vapor and the liquid will be existing. And if you look at like this is the substance, as I told earlier that it will contract on freezing, unlike the water. The water will be expanding on freezing, that is why density became lower and the water will be floating on the ice will be floating on the water, right. So, if you consider, I mean from this figure, if I take this pressure and temperature, you will get a line here and that is basically liquid and vapor, and this is your solid and vapor and this is your solid and vapor line. And of course, if you do that P and V, I mean if you look at from this side, it will be plotted like this, and this is liquid and vapor. As I told, this will be triple line, this is the liquid region, there will be solid and liquid region and there will be solid region. And this will be what you call valid for most of the substances except water, right. Now, we will consider another situation that where liquid will expands on freezing, that is water, and it will be having what you call the similar features, like it will be having solid in these regions, right, and there is a liquid vapor region and this is a solid vapor region, and of course, this is the vapor region and this is your critical point. If I just plot it here, the pressure and temperature, like it will be having similar, like liquid and vapor region line and this is solid and vapor region line. But here this has been changed as compared to the previous one, that is a solid vapor line, it has been slope has been changed. Earlier it was like this earlier and it has been changed. So, if you look at this line, if I plot this from this side, that is from this side, if I plot, I mean if I look at from this side pressure and the volume, I will get, this is basically volume. So, I will get the liquid vapor region here and this is the vapor region. However, and this region it is a different, you can't have, it will go directly kind of things from the liquid vapor and you will get solid here. Of course, in this region it will be solid and liquid, and that is the liquid region. Therefore, because it is expand on the point, that is the region y at what you call below this point, it will be go directly to the solid. And as I told that like let us look at this phase diagram of water, which is quite interesting, and because the ice will be at total maybe something around 7 in a solid ice will have 7 phases, right. Similarly, if you look at your carbon, carbon will be 2 phases, right, like your diamond and then what you call carbon, right, and graphite. Sorry, there are 3 phases, the carbon, graphite and diamond, 3 phases. Similarly, you can think of liquid helium, like it will be having 2 phases. So, here the solid ice is 1 here, and then if you look at this is also a triple point, right, I can think of about a triple point here. And in this case, if I consider this as a triple point, one side is solid, another side is solid, another side is liquid. But if I consider a here this point as a triple point means 3 points are joining, right, 3 phases are existing together, right. So, one side is solid, other is solid, other is solid. So, it is really possible, and similarly one can think of also any other points here. This will be 2 solid and then liquid. So, I thought that I will show you this diagram, which will be quite interesting, that ice is having 7 solid phases. So, this phase transformation, what will be knowing from the one phase to solid to the another, we can call it basically solid allotropic transformation kind of things. So, let us look at the phase diagram of a carbon dioxide, right. It is similar in nature, but if you look at this is having a little difference here, like it is moving this way. Generally the diagram will be like that, but it is going this way. But the important point is here that if you look at this triple point, right, where all these 3 phases existing, it is, if you look at this pressure, right, this pressure is above the atmospheric pressure, am I right? But whereas the water, it was below, right, because the atmospheric pressure is something around here 100 kilopascals kind of things. Now, if you just at the atmospheric pressure, if you are in what you call solid, right, and if you it can be converted directly into the what you call the its ice, because it will be in the ice form, right. So, if I consider this as atmospheric pressure, the gas it can be converted directly into the solid form, and at a temperature, if you look at it, is something less than 200 Kelvin, right. If you look at this temperature at which the phase change will be occurring is basically less than 200. That means, if I extract the heat from the carbon dioxide at atmospheric pressure, right, and if it reaches something less than 200 Kelvin, then it can convert it directly into ice. We call it as a solid carbon dioxide or dry ice, right. So, that is why I mean like that is being used using this carbon dioxide, and one can think of. So, and all these properties what we have seen in basically what you call the temperature, pressure, kind of things, and then specific volume. But however, thermodynamic properties we need to talk in terms of entropy and enthalpy, because for our analysis we need, and that properties can be shown on the HS diagram. The H is the enthalpy and S is the entropy, and this diagram was made by Dr. Richard Moylier. Therefore, this diagram is known as the Moylier diagram, right. And so, this diagram will be looking like that. H is plotted here with the S entropy. If you look at, this is your saturation line, this line corresponding to saturation line here, and this is your vapor line, vapor gas or the vapor here, and in this case this is the weight mixture. Of different quality, like 0.7, 0.75, 0.8, it goes on, and this became a saturated line, x is equal to 1. And if you look at, this is all corresponding to different pressure, like you can say think of like 10 kPa here and 20 kPa, it goes on increasing till 10 megapascals. Earlier days we used to this diagram to evaluate the properties. For example, if I take the pressure, a particular pressure line, let us say 200 kPa, right, and if I know, let us say, some weight fraction. For example, if I take a 200 kPa, if my weight fraction is here, right, and this is the isobaric process, right. I will go from quality of 0.95 to, let us say, I will go to the 0.8. I am moving here to, let us say, 0.858, right. So, what is happening? I can get directly enthalpy in this point. So, this enthalpy change will give me basically how much heat is being added, or it is being what you call, there will be change in enthalpy. That enthalpy I can get directly from this chart. And what are the problems I will face with this? For example, if you find out that your X, the quality is not 0.95, it may be 0.96, right, then you will have to interpolate and do that, and then there will be lot of error involved in that. So, that will be, but you can get quickly the data from this plot and evaluate it, and you can also feel what is happening at a constant pressure and other things you can think of. It is not only the constant pressure one can think of, one can find out what will be the isentropic process from here. For example, I can move from this point and say that vertically I can go down and say that what will be my these things and what will be the pressure. I can get all the data from here, right. What will be quality if I go down, and if I know that like how much I will be, then I can get what will be the pressure, what will be enthalpy, all those properties I can get from this diagram, that is the Moeller diagram. Earlier days these diagrams were being used very much, but nowadays it is being less used because it is little bit inaccurate to this thing. And this, but however, this diagram will be helpful to visualize what is happening instead of doing some mundane calculation. So, keep in mind that critical point is not shown in this case, but however, if you look at a bigger kind of things, one can think of using that. So, what are the disadvantages with the graphical data? Because what we are looking at, not only the processes, from this we can find out graphical the data, and which will be useful for our calculation. The value, as I told, the value from this diagrams or the Moeller chart or any other kind of diagrams will be not very accurate, but as it is difficult to read properly, So, therefore, that is one disadvantages. The interpolation of data, as I told you, that suppose you want to evaluate the quality at 0.96, however, in the diagram it is given as 0.95. So, therefore, if you want to, then it will be inaccurate, you will have to approximate in a paper. So, that will be leads to the loss of accuracy of the data, and limited number of data can be presented in a diagram. You cannot put all the things because it will be very clumsy and cluttered. So, therefore, that is the limitation, and for most substances the relationship among thermodynamic properties are too complex to be expressed by the simple equation. You can say that why not to express in equations, that is really little difficult to do that, but however, as we are progressing, maybe we can find out a data or a relationship which can take care of that. So, that is an open challenge to have a at least semi empirical relationship which can be utilized, but till now people are not successful in giving expression which will be accurate enough to be used for the calculation. So, some thermodynamic properties can be measured easily, as I told, like pressure, volume, temperature, this can be measured easily. But however, there are several which cannot be measured. For example, like your entropy, Gibbs free energy, Helmholtz free energy, and enthalpy, internal energy. So, those can be really calculated by using the properties which can be measurable, or measured properties can be utilized. But we need to have a relation between these things, and which we will be discussing little later on. By that one can do that. And the partial derivative of property is not readily available. So, whose estimation is quite difficult to lead to the loss of accuracy, because these graphical data one can think of like using for particular pressure, particular certain measurable properties, right. So, then if it is not available, then you will be will be trouble, and also there will be loss of accuracy. Therefore, that is the reason why the properties are frequently presented in the form of tables, right. Because of these disadvantages, we need to keep the data on a tabular form, and which we will be discussing, particularly the steam table and the refrigeration table, and I will be discussing more the steam table. In your tutorial classes, refrigeration table will be discussed. So, let us look at this property data in a tabular form, and as I told that properties are frequently being kept or presented in the form of tables, so that it can be easily utilized. And as I told earlier that these properties, measurable properties, can be utilized for finding the what you call non-measurable properties, of course using the thermodynamic relations. And the result of these measurements and calculated values of this all the properties can be presented in a tabular form in a convenient format, because format is also very important, and how you are presenting the data and how it can be extracted. Let me tell you that I have already talked about enthalpy, but the implication of enthalpy is that it is the combination of property which we use in our flow systems. As I discussed earlier that we are using the control mass system and control volume system, or the closed mass like kind of things, we call it as the open system, where the flow will be taking place. In that case, we use basically the internal energy, let us say at station 1, if I say this is station 1 and this is station 2. So, it will be having certain flow work, that is P 1 V 1, and otherwise the flow will not move, and it makes the flow to move. You can think of as if a piston is there and it is pushing the fluid to get into this, and also it is going out. We will be discussing that little later on. So, also it is with leaving the fluid is leaving this control volume with the internal energy U 2 and the flow work of P 2 V 2. So, that together combination of this U plus P V being utilized in the open system, and we call that as a enthalpy, right. And that if you look at this P V is basically the unit is joule, and if you look at this is basically you can think of pressure is kPa, and unit of the volume is meter cube, that became kilojoule. And if it is the specific volume you use, if we use the specific volume, right, and that is meter cube per kg, which is multiplied with the pressure kPa, you will get the kilojoule per kg. And you can think of using in FPS unit, we call it BTU, British thermal unit, and that is PSI, pounds per square inch, into the feet cube, that is multiplied. So, we will be using not only as I told that the enthalpy, but rather the specific enthalpy, which is basically per unit mass. So, the steam table which we will be using very frequently for getting the data for solving the problems kind of things. So, it can be represented in tabular form in the following manner, but however, before we could look at it, we need to understand how many variables we can put and what will be the format of the steam table. For that, we will have to use the Gibbs phase rule, that is F is equal to C plus 2 minus P, and F is the degree of freedom and C is the number of components what you need to represent, and P is the phase. So, if you look at for steam, the component wise it will be water, right, component wise will be water. So, therefore, C will be 1, but there might be several other things, like let us say if you look at your petroleum, right, products, it will be having several compositions, right. So, therefore, their composition will be need not to be 1, it will be several of them, right, at different kind of things it will be there. So, and we let us consider that we are interested in what you call two phases, liquid and vapor. That means the phase will be 2, right, and then what will be the degree of freedom? Degree of freedom will be 1. What is the meaning of that? That means for the complete specification of a state of a system, right, when we are talking about two phases and what you call the single component substance, then one independent thermodynamic properties, either pressure or temperature, is sufficient to describe the system, right. So, therefore, that is the reason why we will be using, and knowing this thing we can find out the properties like internal energy, like your enthalpy and your entropy and so on, like Gibbs free energy, Helmholtz free energy, right. But however, these properties cannot be really measured directly, I have told several times, and which can be related to the energy, change of energy of system, and this derived data can provide the values to the change in internal energy, change in enthalpy, change in entropy, but not the absolute values, right. Absolute values you cannot really assign to these quantities, and hence we need to have a reference state, and generally this reference state should be chosen such that these numerical values must not chosen, and such that these certain numerical values must be assigned. That means you need to assign certain values to the reference, the way we have done for your what you call temperature kind of thing. So, reference point for is taken considered as a triple point of water for these substances. I mean, if you look at the steam, and and that is corresponding to temperature of 0.01 degree Celsius and pressure of 0.6113 kilopascals. At these conditions, like entropy and the internal energy, enthalpy, kind of things can be considered as 0, and then we will go to change that positions and then get the values. So, choice of this reference point does not affect the actual data, right. You can have a different, but this is internationally accepted triple point as a reference point. As a change in thermodynamic properties is basically required. So, therefore, we have a reference point, and then from that you will evaluate, because what we will be getting is a delta u. So, therefore, you should have a known reference point and then you will calculate what it would be. So, let us look at the typical thermodynamic properties of the saturated steam, and we call it as a basically pressure, because the pressure is a variable. If you look at, I have given 1 kilopascal here and 10 and then 100, 200, 2000. Of course, this is a very large 22,000, 120 kilopascals kind of things. So, of course, if you look at, this is not given this interval, larger interval, it is not given in a very uniform way, but if you look at actual table, like it is given as a closer interval, right. So, that you can get the data. And what you can note here, let us say 1 kilopascal, if I take, temperature is very, very low, like 6.98 degrees Celsius. If I take this, this temperature is basically corresponding to the saturated temperature. If I take something 10 kPa, this is 45.8 degrees Celsius, and this Vf is what is happening here? It is goes on what? Goes on increasing. Am I right? Very slightly, because it is a compressible liquid, so therefore, that is not much change. But however, if you look at this Vg, that is specific volume of the vapor, it is goes on decreasing at a very rapid rate as compared to the liquid, because this is compressible in nature. And if you look at the enthalpy, this is the enthalpy of the liquid at that pressure of 1, and enthalpy of gas, this 2514.54 kilojoule per kg, and this enthalpy is goes on what you call increasing, and this is basically, if you look at, that is it is also goes on increasing kind of things. And if you look at the change in enthalpy is, latent heat of vaporization is goes on decreasing here, right. If you look at here, it will be very high and here it will be very low, and keep in mind that this corresponding to the pressure of 22,120 kilopascal, that is megapascal 22.1, is corresponding to the what you call critical point, where this specific volume of the vapor, specific volume of the liquid is same as that of the specific volume of the vapor, the same, that is the critical point. So, let us look at the another table what we will be using, we call it as a temperature table for saturated steam. Here in this case, what is given is the temperature and corresponding saturated pressure, and the first one what I have given here is 0.01 degrees Celsius and pressure is 0.6113, and these are the specific volume of the liquid and specific volume of the gas, and enthalpy of the liquid, enthalpy of the gas. So, this basically the your triple point case, and of course, as you goes on increasing the temperature, your saturated pressure goes on increasing, and it reaches a pressure where you are having a what you call the this pressure is corresponding to, if you look at this temperature 374.15 degrees Celsius is corresponding to what? This one is your critical point, because the specific volume of liquid is same as that of the specific volume of the gas, and this is corresponding to where the enthalpy of the what you call the liquid and the vapor is also the same. That means latent heat of vaporization at the critical point is 0. So, now what happened, suppose we are having a table here. Of course, it will not be, as I told, it will be not that interval, that big interval, large interval. So, it will be nearby, but let us say we are having 10 degrees Celsius and there is another temperature 20 degrees Celsius, but you want to evaluate at the, let us say 15 degrees Celsius saturated temperature, what will be the properties. So, how we will go by that? What we will be doing, this is not really linear, but we take a linear interpolation. If we could have in the relationship, so if you look at this table, this data like all these are not linearly fitting, otherwise you can have expression and then do that very beautifully. You need not to have a worried about the steam table or the refrigerant table and put the data in a tabular form if it is linear. Keep in mind that the relationship between these data cannot be expressed as a linear form, but however, we will be using a linear interpolation between the two data points just for the approximation sake, and this is an approximate because we do not have any better way. As the interval will be small, that is good enough to take a linear interpolation. For example, like if I take this there is a temperature here correspond let us say 150 degrees Celsius, and I can have a properties from the table I can get 0.3924 what you call meter cube per kg, right, and this is known. So, if you look at this is known, right, this point is known and you will be knowing either temperature, so that you can find out the specific volume, and if you know this temperature you can find out the specific volume at this point, but you need to find out what will be the specific volume here. That means, for that I need to find out, I should know the temperature, then I can find out specific volume, right. For that what we will do? We will have to use this slope because this is a linear, this slope is same as that. So, I can say T minus 100 is divided by the 1, right, because that is at 1, and this as 0.393 is equal to 150, like if I know this is 150 and corresponding to this specific volume, right, 150 minus 100, and because this portion is known, right, values, then I can evaluate, find out what will be temperature, right. In this case, of course, I know that at this specific volume what will be temperature. There might be a situation you know the temperature and then you can find out what will be specific volume, right. Vice versa you can do. So, of course, if you look at, like if you want to handle the saturated mixtures kind of things, then you can find out the quality, and from knowing these qualities you can find out the specific volume, right. And if I know this what you call from the table, if I know this internal energy or the enthalpy at the saturated liquid point, and if I know this HFG, or if I know this Hg, right, if I know this Hg, Hg is basically saturated vapor enthalpy, and then from that I can find out HFG. HFG is nothing but your Hg minus Hf. So, if I know this, if I know this one, then I can find out that by knowing this quality I can find out enthalpy for any quality. Similarly, I can find out entropy and other properties like internal energy and other things. So, let us take an example, like, and to illustrate how to use the steam table, like in a piston cylinder assembly 1 kg of saturated liquid water is vaporized completely at 100 kilopascal, and we need to determine the volume change and amount of heat energy added to the water. So, that is the this thing what we need to do. So, if you look at the mass is 1 kg and pressure is 100 kPa, and we need to find out change in volume and enthalpy. So, how to go about this? Let us say change in volume, how we will do? Basically change in volume will be change in specific volume into mass, that will give me the what you call the change in volume. So, what in this problem what we know basically at 100 kPa this point is known, this is basically saturated what? This is saturated liquid point. From the table of if I look at 100 kPa, right, I will be knowing what will be Vf, and similarly I can find out what will be because saturated vapor, right. I am saying that this in this problem what liquid water is vaporized completely, that means this point. So, if I know this Vg from the table, I can very easily find out the change in what you call the volume. So, if you look at from saturated steam table at 100 kPa, we can get these values. Vf is very, very small. Keep in mind that this is 0.001, you can say 0.43 meter cube per kg, is a very, very small. And Vg is of course very high, that is 1.6949 meter cube per kg. We can find out also Hf, which is 417.46 kilojoule per kg, and Hg is very high, that is 2258.01 kilojoule per kg. And if I know these values, right, I know these values at 100 kPa. So, from the steam table, then we can find out very easily, that is delta V is nothing but m into Vfg is equal to m into Vg minus Vf, right, and you just multiplied the difference because it happens to be 1 kg. I have taken an example which is a simpler one. So, that the change in volume is 1.69 or 1.7 meter cube you can think of, right. So, similar way we can find out the enthalpy change during this phase change process. This is basically phase change. So, it will be same as that H or delta H is equal to m into Hfg is equal to m Hg minus Hf, and Hg and Hf is known. See, this is known because this is nothing but your these values, and Hf is known, this value is 417, you substitute these values, you will get this amount of kilojoule. So, we will stop over here, and we will be taking some few examples in the next lecture, how to use the tables and what are the problems associated with it, and later on we will be moving into the also how to talk about the gases or the relationship. Thank you very much.